Hi class, here we go with today's video, or part one of the videos. We're going to talk about diagonalization. So basically what we're doing today is we are taking a matrix and we are factoring it into three parts. Okay, so diagonalization is one of the matrix factorizing methods. The pieces of this factorization are really important. We're going to be using eigenvalues and eigenvectors. There's a few ways to diagonalize, factor matrices, and they're all kind of important in their own way, but this is a very, very common method. We will be diagonalizing matrices quite a bit after this, right? So I know I say that every time, but every time we learn something, it rolls over into the next thing that we learn. Linear algebra it's like a snowball, right? It kind of started small and it just keeps picking up things as we go along, and we just keep expanding on the topics that we keep using, right? So this is the next thing. So just like the last video, the eigenvectors and eigenvalues, we used this idea of bases and transformations. We're going to use that same sort of things. So we use bases and transformations to talk about eigenvalues and eigenvectors. Now we're going to talk about eigenvalues and eigenvectors and how we can use them to, in this case, diagonalize a matrix, right? And then we're going to just keep progressing in that fashion and talk about how we use the previous things to come up with new interesting things in linear algebra, right? So let's go ahead and get started. The definition of a diagonalizable matrix is that we have to have a square matrix, right, n by n, and it will exist if we have a diagonal matrix D that is invertible. The diagonal matrix is coming from A, and we have to have another matrix P that is invertible. So our diagonalization is going to be a P, D, and a P inverse. So P has to be invertible, and that is how we diagonalize our matrix. So our matrix P, which we'll talk about how to find, our diagonalization of A and P inverse, this is a factored form. So it's three matrices that if you multiply them out will give you back your A matrix. Okay. So our diagonal matrix D has entries along the diagonal of the eigenvalues of A. Okay. And P is made up of the eigenvectors of A. So we have to find the eigenvalues so that we can make the diagonal matrix, and then those associated eigenvectors is how we form that P matrix. Okay, and of course remember P is going to be linearly independent because those vectors make up a basis, right? So they are going to be different from each other. Okay, so this matrix P is formed by the eigenvectors associated with each eigenvalue. So I have lambda 1, lambda 2, up to lambda n, and notice that this goes in the same order as I describe my eigenvalues. Okay, so they go in the same order. U lambda 1 is the eigenvector for this eigenvalue, and so forth. So we put these column vectors together to form a matrix, and that will be our matrix P. Okay, so let's start off with an example. In this example, we're going to use the matrix that we had from our last video. Okay, so when we're doing our eigenvalues and eigenvectors, I used this matrix as our example matrix in order to find the eigenvalues and eigenvectors. So if you want to, you can go back to that video, but we will summarize what we have. Hopefully you're familiar with how to do that, because I'm not going to do this all over again because we've already done it. If you want to, you can pull up the write-up or actually look at your notes, right? Because you should be taking notes as we go through this. So look back in your notes. I'll give you a second. You can go backwards, I don't know, a page and a half, 2 pages, depending on how much you write in your notebook. But you should see the eigenvalues for this and the eigenvectors for this. Okay, we'll summarize that now, but we did do this as our example in the previous video. Okay, so what we have is we were able to find the determinant, okay, through whichever method you like, cofactor expansion or the column form where we repeat the two first two columns, and then we, multiply across the diagonals. But regardless, when you simplify that down, you should get out this characteristic polynomial. This characteristic polynomial being 0 gives us the eigenvalues that we want, right? So 0, negative, positive 2, and positive 1. Okay, so we found that last time. And we also found the eigenvectors that were associated with each one. So for lambda 1 is 0, we had this eigenvector. For lambda 2 equals 1, we had a very similar looking eigenvector, but instead of 3s, it was 4s. Okay, so again, these are linearly independent. And for lambda 3 equals 2, we got our third eigenvector, which was this. If you notice, these are all linearly independent from each other. Okay, this is a basis for this eigenspace, basis for this eigenspace, and this is a basis for this eigenspace, but they are all also linearly independent from each other. Okay, so my diagonal matrix is made up of the eigenvalues. Okay, first one, second one, third one. Everything else is zeros because that's what it means to be a diagonal matrix, right? A diagonal matrix only has entries along the main diagonal. Okay, so my P matrix is made up of the individual eigenvectors. Okay, so here's the first eigenvector, the second eigenvector, the third eigenvector. Notice that these are in the same order. This first column is this eigenvalue, and its eigenvector is in the same place. It's the first eigenvector I use. The second column contains the second eigenvalue, and the second column vector is the second eigenvector. Okay, and so forth. This is the last eigenvalue. This is the last eigenvector. Make sure that they match up. If they don't match up, you're gonna not diagonalize your matrix right. You'll come out with something. You'll basically, when you go to check, what will happen is you'll get this matrix out, but the numbers will be all skewed around in different orders. Okay, or maybe this one is all, this vector is messed up, or this row is messed up. It'll come out close, but maybe you'll have something off. Maybe this will end up being a 0, and all the other numbers are correct, right? So you always want to make sure that you check your diagonalization when you're done. Check this to make sure you get your right matrix, right? So there's always a way to check to make sure you did it right. Multiply these things out in the correct order, and you should get out A. Okay, so let's come back to where we were. So my inverse matrix is just the inverse of this, right? It's a 3 by 3. If this was not linearly independent, I would have a determinant of 0. I would not be able to find the inverse, right? So that's one thing that if you got it wrong, is if there's no inverse that exists, okay, then you probably messed up on your eigenvectors, because your eigenvectors all have to be linearly independent from each other, right? Otherwise, this P matrix would not be invertible. Okay, so here this is just a statement saying what I said before. Note that the eigenvalue column vectors, okay, here in D, coincide with the placement of the eigenvectors in P, right? So again, the first eigenvalue, first eigenvector, second, third. Okay, this is just the inverse of that. There's no real connection between this. Okay, these two are the ones that are connected. So for PDP inverse, I will have this times that. Right, so again, once you find your eigenvalues and your eigenvectors, the rest of this is just making sure you put it in the right order, right? So I've got my P first, I have my D diagonal matrix, and my P inverse. If I multiply these out, I will get my A matrix back out. Now again, if I had messed something up, maybe I switched these two columns, or maybe I accidentally switched these two columns, I'm going to get out something very, very similar, but it's going to be off slightly, right? One number is going to be off, two numbers are going to be off, a sign will be off. So just make sure you check that your diagonalization brings you back to your correct answer, okay? Always check. It's a very quick check. especially now since we're allowed to use calculators for everything. Just plug these matrices into your calculator, multiply them out, make sure that you get this correctly. And also make sure you put them in the right order. If you switch these things, you're going to also have this all messed up. In fact, you'd probably end up with the inverse matrix of A, I believe. Okay, I think we can talk about that later. P inverse D. P will give you, I think it gives you A inverse. I'm not sure. It's been a while. We'll cover that when we get to that section. Okay. So notice that this is A, right? So this is the matrix we started with. So that is how you diagonalize A. So I know it seems like this was really short, but remember, you guys, we had a very, very long discussion about how to find the eigenvalues and then find those eigenvectors. So that's the hard part, right? Especially for 3 by 3, you're going to be factoring some third degree polynomial in order to get these values out, and then you have to put them into your matrix to get this. So the eigenvalue and eigenvector portion is what takes a long time. Okay, after you've done that, then the diagonalization part is very, very fast. So we will do a full example where we start all the way with A and then find the eigenvalues, the eigenvectors, and then so forth. Okay. So it's just easier to do this because we've already found these values. Okay. So in short, I can say that PDP inverse is A, right? So that's the diagonalization of my matrix A. So let's think about this, okay? I think I said last time that any scalar multiple of these eigenvectors is still an eigenvector. So I could have turned this from 1/3, negative 1/3, 1 into all whole numbers, this into all whole numbers, and this into all whole numbers. So what we're going to do next is I'm going to show you what would happen if we change this into an equivalent vector that's just a scalar multiple, right? So that I don't have fractions. I know some of you guys, most of you guys probably really don't like fractions. I always just stay with fractions. It's less work that I have to do, right? One more calculation is just another possibility for me to introduce some error into my calculation. So I just keep with whatever my end result is, okay? Also later on, we will be using these things. The result that we get out in its basic form here, right before we start to like use scalar multiples, this is going to be useful for later. So, you know, it's just a good habit just to keep it how it is. But there's nothing wrong with scaling it up so that they're all whole numbers. Again, right, I'm a math professor. It's not going to throw me off. I'll be able to tell if it's equivalent or not, but you should be able to do the same thing. Okay, so here we would multiply everything by 4, so I get this matrix, and for this one I should multiply everything by 5, because then that'll give me 2, negative 1, and 5. Okay, so we're just going to use the scalar multiples of these eigenvectors so that they're whole numbers, right? So my P matrix, instead of being a bunch of fractions, it's full of whole numbers, right? Which is nice. Generally, when you do this, your P inverse ends up having a bunch of fractions, but in this case, that wasn't the case. All whole numbers and all whole numbers. So now when we diagonalize, everything is in whole numbers, which is nice. It's easy to read, it's easy to work with, and that's fine. There's not a problem with that, right? So this will also work to diagonalize our matrix A. Go ahead and check that for yourself, right? So your B matrix will stay unchanged. I'm sorry, your D matrix, it's the same diagonal matrix. You don't change those values at all, okay? So that brings us to a new theorem, which is if A is n by n, right, n by n matrix, then A to the k is P D to the k P inverse, right? So if I want to find powers of my matrix, instead of going A times A times A times A times A times A, I can do that with the same eigenvector matrix and just raise D to a power. Now you might be saying, well, that sounds like more work because I have to still, you know, exponentiate some matrix, but it's actually easy to exponentiate a diagonal matrix, okay? And I know it's a lot of work to find P and P inverse, but if you think about this, you can now find any power of A. Once you have P and P inverse, you can also do lots of other things that we'll talk about later with P and P inverse, right? So finding these things is it just helps us to do lots of calculations, which you should be aware of, because most likely on our final, depending on how it works, is I'll give you one matrix and then I'll say do these 10 different things to it. Maybe you raise it to a power, maybe do all these other things, where finding P and P inverse will help you to do all of that a lot, right? It'll make that process a lot easier. So let's take an example. Okay, again, our same matrix, because we already have P, D, and P inverse, so it just makes sense to stay with the same matrix. So find A5. Now, of course, you could just plug into your calculator. Here's my matrix, raise it to the 5th power, and it'll give you an answer, and that's great. There's nothing wrong with that. But again, if we come back to regular class and I'm like, hey, here's a calculator portion and a non-calculator portion, you know, you might need to be able to know how to do this, right? Not only that, but we can use these in proofs and things like that later on, because this is a property of the diagonalization of a matrix, right? So for A to the 5th, I need P. There's an error here. This should be D to the 5th. I thought I got all the errors in the write-up for this one. Apologies, you guys. But A to the 5th is P, D to the 5th, P inverse, not A. Okay, so I have my P, my D to the 5th, and the P inverse. Now watch how we do the 5th power of a diagonal matrix. It is very easy. You just take the 5th power of each of the entries, right? So 0 to the 5th is 0, 1 to the 5th is 1, 2 to the 5th is 32. That would not be the same thing if I were to take, for instance, this to the 5th power. This to the 5th power will be very, very, very annoying, right? But the way that diagonal matrices work is, again, very similar to an identity matrix, right? Except that the diagonal is not all ones; it has entries in it. Okay, so an exponential form of a of a diagonal matrix is very, very easy to compute. Okay, so if I multiply this out, which is an easy calculation compared to this thing times this times this times this 5 times. This is much easier. It's just 3 matrices. I can find this, right? So again, if you start to get into coding, computing power, computing time turns into a big, big, big issue. Here, to find A to the 5th, if I took this to the 5th power, that is a lot of computation energy that needs to take place, because there's lots of row multiplications, whereas this is a very, very, very simple thing to compute. It does not take a lot of computing energy, so your processing time is a lot smaller, right? For us physicists and engineers in here who will have to start coding models and things like that, right? So that's our example. Okay, so we have another theorem here. If an n by n matrix, a square matrix, has n distinct real eigenvalues, then the matrix is diagonalizable, right? So what this is saying is, as long as there's no multiplicity in your n by n, you're gonna be able to diagonalize that matrix. Okay, so if you do have multiplicity, it's kind of a yes or no kind of situation. You're gonna have to kind of check, right? There's not a quick way to say yes, this is diagonalizable, and no, this is not, right? So that's what our examples are going to be today. Okay, let's take an example. Right, let's do this from scratch. I have this matrix A, and I need to diagonalize it, so I need to find the eigenvalues and the eigenvectors first, right? So remember, the way that I find the eigenvalues and eigenvectors is a little different than most textbooks, and that's because we do it in the opposite direction so that we don't have to factor out a negative of everywhere. If you want to do it the way that your textbook does it, that's fine, but I find that this is easier. There's less complications this way, right? So I'm going to find the determinant of lambda I minus A. If you go and look at any textbook, it will generally say A minus lambda I. They're equivalent, as you can see. It doesn't matter, but this way it looks more like a polynomial versus 3 minus lambda, right? So just remember to take the negatives of all the things that are not on the diagonal, Okay, so all of these values are opposite now. Okay, 3, -5, 6, these are all opposites. And then there'll be lambda minus your diagonal entries. So finding this determinant is, if we do it in the column method, right, which I find is a little bit easier, right, you just go across these diagonals and across these diagonals. Okay, so we have these three, 1, 2, 3, and then these three, which is 30 and a 3, so that's 90. And then that same thing again, 5 and 6 is 30, and another 3 is another 90. And then I'm going to subtract this one, so 25 and lambda minus 2, but there's two negatives, right? And then negative 18 being subtracted, so it's a positive 18 times lambda 3. And then here's another 18 and lambda plus 7. Okay, so that's where these come from. Again, I'm going to talk through this semi-slowly so you have a chance to write this down as we go through the problem. Okay, so this is what I have, and so in my next step, what I'm going to do is I got to simplify this. Okay, so I can obviously add 90 and 90 together. I can distribute these things. You can distribute them and simplify them if you want to. I think I weighed on that. We'll see. I don't remember. I wrote this a couple days ago. And then I want to expand this out, right? So, you know, I could just be like, hey, you guys, this is the end polynomial, but I'm trying to walk through this like we were in a lecture, right? So what I'll do is I'll multiply two of these together first. One of these two, I don't remember which one. I guess it was these ones. Okay. So I multiply these two together first. Okay. I combine these. I expand this. I expand that. I expand that. Right. So it's much easier. Just go slowly. Again, I want you. We don't have a regular class, so I want to make this as easy to follow as possible. So again, I'm gonna talk through this slow so you have time, which is why I am rambling right now. Okay. So on the next line, we want to multiply this out and combine these things. You know, I have a minus and a plus, so that goes away, and I'll have a 25 lambda. This will be negative 104 plus this is a negative 180, I believe. Okay, so I multiply this out. 3 and 14 is the 42. So I'm left with 25 lambda and 50 from here. Okay. All right, so 104 minus 126, that's 2 something, right? And then the 180, so that's 230, minus 230, and 180 is minus 150. 25 lambda was the only one that's left. And then these, right here, up to 42, is from this expansion. Right, so now I can combine my like terms, the square terms, the lambda terms. I got a minus 29 here, plus 25, so that should be negative 4. And I have my cubic. Okay. I posted a video for how to factor basically any size polynomial as long as it has rational zeros. So hopefully you guys watched that, or hopefully you already knew how to do it a little bit using synthetic division and the rational zeros theorem. It's going to be very, very useful. I didn't know I could do that. So here, though, is actually easy. I can do this by factor by grouping. I can pull out a lambda squared and a 4 here, and then I'll have a lambda plus 2 and a lambda plus 2, right? So I can actually factor by grouping for this one. That's not normally the case. It does not normally work like that when you get to a cubic, but for this one it does. Now I have a common term of lambda plus 2, and this is a difference of squares. So then it's very easy now for me to find my zeros, and if you notice, I have multiplicity. Okay, so again, we're showing here we know that when there's distinct eigenvalues, when they're all different, for an n by n matrix, it's going to be diagonalizable. So now we're exploring when they are not all distinct. That's basically what we're doing. Okay, so this example and next example will have multiplicity. So I have an algebraic multiplicity of negative 2 twice. So it looks like I messed this up. There should be another negative 2. That's okay. You guys are smart. You can catch that, right? So for lambda equals 2, I only have 1, right? I only have 1, not 2, only 1, because I messed up here. There should be 2 negatives here. So this one only appears once. So here it's written wrong, but the math will be right. There's only 1. Okay, so what this implies is now I'm going to take in here and I will have 2. So 2 minus 3, 2 minus 2, 2 plus 7, right? So negative 109, everything else is the same. And I need to solve this. Again, you can set it equal to 0 if you want to, but it is not necessary because they don't do anything to each other, right? So I can put this in my calculator and go down to my reduced row echelon form, and I will have this matrix, right? So here's my free variable. So x2 is negative 2/3 x3, x1 is negative x3. Okay. So then that'll give me out my eigenvector, right? If x3 is 1, x2 is negative 2/3, x1 is negative 1. Okay, so that's my eigenvector. For the next one, I have lambda 2 is same as lambda 3, which is negative 2, right? So again, I have 2 negative 2's, so that's my lambda 2 and lambda 3. Okay, so both of those, oh man, I guess that didn't go as a subscript either. So this is negative 2. Okay, so that gives me this matrix when I plug it into the diagonals, right? Only the diagonals are different. If I throw this in my calculator, I get this out. So that means that x2 is 0 and x1 is negative x3. Okay, so this is my x2, and if you notice, there is no third eigenvector, right? So remember in the last video, sometimes you get out 1 when you have algebraic multiplicity. Sometimes the geometric multiplicity is equal to the algebraic, meaning if this is a double root, sometimes you get 2 vectors. That didn't happen in this case, right? So here my P matrix is 2 vectors that have 3 entries each. It is not n by n, right? It's not an n by n matrix. I can't find the inverse of this. There's no way. It has to be a square matrix in order to be invertible. So if this is not invertible, it's not diagonalizable. Okay, I can't find the diagonal of that matrix A, right? So your classwork is to diagonalize this matrix. Okay, so I have a link for you. I'm trying to clean up your canvas a little bit. So this is a classwork problem. It's due at the end of the night, okay? Because if we were doing this in class, then I would say, hey, do this in class and hand it to me, okay? So by midnight tonight, I need to see this written up, okay? I will send that in an email to make sure you guys get through this, okay? So again, Tuesdays are the days we have lectures. We're going to run through it like was a regular class. I'm going to try to make these videos kind of early, which is, it's actually like 3 o'clock now, but it's going to take me about 3 hours to finish making this and upload it. So hopefully these are up by 6 o'clock for you guys, okay? So make sure you enter this. It has to be as a PDF. Again, I like the app Cam Scanner, CAMSCANNER. I'm sure I wrote that in an email already. I'll put it in the email where I write this information. It's a really nice app. That's how I post your solutions and things like that. Okay, so upload this for points for today. That way I know you're watching the videos and you're staying current on what we're doing. All right. Hope you guys are not going too crazy through this break. I know I am extremely busy and very bored at the same time. So hopefully you guys are doing okay. If you would like to have some conference time, you can request office hours on the discussion board that I have at the very top of Canvas. My Zoom does not work. We can Zoom on my phone, but that's not gonna help me to like do math with you. I guess I can videotape myself or Zoom myself writing on a piece of paper, but on my laptop that the campus gave me, the camera does not work for Zoom for some reason, right? So if you really want to see my face, we can do it through phone. If you just need to talk to somebody, then you can Zoom through my laptop. Let me know. We can set up an appointment, an office hour appointment, and we'll work out the details. Okay, so hope you guys are doing okay.